My name is Mohammad Yasir Slim. Today, me and my group members will explain you about the CCP problem of our PDC course, which was a real life problem basically, in which the distribution in one dimensional rod over the time due to heat conduction. तो ये प्रॉब्लम हमने 3 फेजेस में पहले डिवाइड की, मतलब सब प्रॉब्लम्स में डिवाइड किया इसे. Our basic goal was to model how the temperature changes over the time using different numerical methods and parallel computing techniques. So we divided this problem into 3 phases. First one was developing the mathematical model and validating its serial code, and then its implementation. The second phase was designing the parallel algorithm and planning how to divide that problem for parallel processing. And the third one was implementing and optimizing the solution by using OpenMP and MPI and CUDA etc.
Assalamu alaikum. Hi, I am Muhammad Junaid Ilyas. I will explain the mathematical model and serial implementation. The heat conduction in the rod is governed by heat equation, which is fundamental equation in physics. It describes how the temperature at any point of the rod over time due to heat diffusion. In simple terms, it says that rate of change of temperature of a given point is proportional to curvature of the temperature distribution around that point. We use FDM finite difference method to convert his equation in numerical form that convert the solved on a computer. The key idea to approximate that continuous temperature distribution by dividing the rod into discrete points. I am discussing about the serial solution. We wrote the code into C++ implement to a serial solution. In a serial solution, we iteratively updated the temperature at each point along the rod. This allow us to verify that model we work correctly and gave us a way to compare a parallel implementation later. Assalamu alaikum. Hi, my name is Muhammad Junaid Ilyas, and I'm discussing the challenges we faced and we explained and how we explained the parallelization of our solution. The main challenges we faced in data dependencies, boundary exchanges, load balancing, and synchronization. Data dependencies: the temperature at a point depend on temperature of its neighboring point, which complicates in parallelization. Boundary exchanges: when divided the rod into segment, each segment must exchange boundary data with its neighbor. This lead to communication overhead between process or thread. Load balancing: to get good performance, it's important that all processes or thread do roughly the same amount of work. Synchronization: in parallel system, we need to carefully synchronize the process or thread to ensure they do not interface with other while updating shared data. We decided three parallel computing technique: OpenMPI, MPI, CUDA. OpenMPI for shared memory application, which allow multiple threads to work on the same system. MPI for distributed memory parallelism, which each process handle a separate of chunk problem. CUDA for GPU accelerated computing, which take advantage of the massive parallel processing power of GPU. I am discussing about next topic: OpenMP and MPI implementation. For OpenMP implementation, we parallelize the inner loop where the temperature update occur by adding a special directive in the code. we instructed the compile to divide the loop into chunk and assign the different thread. I am discussing about MPI implementation. We divided the rod into segment and assign each segment to a different process running on a different computer or processor. Each process handled its portion or to the rod and process communicated with each other to exchange temperature at the boundaries. Thank you.
Hello, my name is Mohammad Zain Ahmed and I'll be explaining the CUDA implementation in our performance analysis. For the CUDA implementation, we took advantage of the GPU's massive parallelism to handle large simulations. Each thread on the GPU was responsible for computing the temperature update for a single point along the rod. This allowed us to process a large number of updates in parallel, which led to significant performance improvements, especially for larger problems. We optimized memory access patterns to ensure that the threads could efficiently access the temperature data. By organizing the computation in a way that minimized memory bottlenecks, we achieved the highest speed up out of all the methods. We compared the performance of OpenMP, MPI, and CUDA, and here are the key findings. While OpenMP scaled well for a small number of threads, it faced performance issues when the number of threads were increased. MPI, on the other hand, scaled well across distributed systems but suffered from communication overhead when dealing with large problem sizes. However, CUDA achieved the highest performance due to its ability to process many updates simultaneously, making it the best option for large-scale simulations. This project not only helped us understand how to optimize heat conduction simulations, but also gave us valuable insights into parallel computing techniques in general. To summarize, we successfully modeled heat conduction in a rod using the finite distance method and parallel computing techniques. We implemented serial and parallel solutions using OpenMP, MPI, and CUDA and analyzed their performance. The results clearly showed that CUDA was the most effective for large problem sizes, while OpenMP and MPI were suitable for smaller problems and distributed systems, respectively. Thank you for watching.